Hi everyone, welcome to this live session. My name is Aditya Bandhopadhyay and I am an assistant professor in the Department of Mechanical Engineering, and I am the instructor for the course on tools in scientific computing. So I first of all would like to express my gratitude to all the students who have taken part in this course, who have actively taken part in the assignments, and basically who have learned something out of it. The whole point of this course was to acquaint each and everyone with the different tools in scientific computing, tools such as those available through Python or Octave. And while we have primarily focused on Python and Octave, it need not be the case. You can extend the logic to almost any programming language that you like. And I hope all of you who are either BTechs, MTechs, PhD students, or even professionals who had a sort of barrier in approaching problems, how to start writing a program for solving or tackling a given problem. So I hope this course has given you some sort of advantage over a previous situation. There have been some doubts on the forum, primarily linked to the plotting and the error that you may find during the plot that you make in Python. And so let me tell you that one of the issues that gives rise to these such kinds of errors is the fact that you don't have LaTeX installed, and the lack of a LaTeX installation gives rise to those LaTeX errors. And I have answered in the forum as well. You can easily avoid that error by simply removing the line which sets the interpreter to text. That is it. So Nitesh says good evening, a very good evening. Please feel free to ask any questions that you may have. I'm more than happy to address them. So one particular aspect of tools in scientific computing that I particularly enjoy is the fact that scientific computing is not just restricted to solving problems numerically, or it is not even restricted to certain domains of science and technology. It can be applied anywhere, starting from biology to earth sciences. And it may strike you that okay, this is a course meant for someone who is doing numerics or numerical simulations, but that is definitely not the case. the fact that experimentalists also require a great deal of knowledge on how to process data, how to analyze data. Now is the age of data science, and it is very important to understand that data hides a lot of information, and it is someone's task to bring out what maximum information you can get out of the least amount of data, because there is no end to data and data is expensive. So the last week of this particular course, which you will see soon, that will deal with various aspects of analyzing or sort of processing various simple experiments and how we can extract certain data that we are looking for. So that is something which excites me as well, and I hope you will find it quite useful. So far we have looked at bifurcation systems, and again, non-linear differential equations. These are not something which someone who is from applied mathematics or even pure mathematics they do, but they find applications in almost all areas of sciences, not just physics or chemistry, but everything. And I hope that through those particular modules you were able to appreciate how with very simple tools you can obtain a huge amount of information. You can understand how systems can undergo transitions and how various system behaviors can change when certain parameters controlling the entire system are changed. So once again, a very good evening, and I'll be taking any questions you may have. Feel free to ask. So one particular topic that we had discussed, and all of the codes are available on the website, was on understanding imperfect bifurcations. Imperfect bifurcations, you may feel that was a very synthetic topic, but let me tell you that it is a very involved subject from the viewpoint of physical systems. And I had given a small example of how a beam bends. So imagine you have a beam under compression. So you can imagine you have a beam or a small stick or whatever. Once you start compressing it, okay, you may think that it's under compression, so the size has to reduce by some amount. That of course depends on the Young's modulus, but after a certain threshold, you observe what is known as buckling. So buckling gives rise to a state which is dramatically different than the condition that you have for pure compression. So any small perturbation in the system will cause it to jump from one equilibrium point to another, and such jumps in equilibrium points are quite common in nature. For example, the populations of various organisms. So you will find that there's a certain population of say certain bacteria, and there is some amount of food that is available, and then nothing's going on, suddenly the population will jump from one point to another. In fact, we have discussed this aspect when we have looked at two things, when we had looked at one-dimensional maps and when we had looked into iterated maps. in such situations you will see that the behavior, while being a very simple system, would be quite competent to actually express what the actual variation of the population will be. And then how do you account for various non-idealities? That is done by accounting various other terms which sort of break the usual symmetry and equilibrium points in the system. And such kinds of breakage of equilibrium points, while we have seen that for the case of pitchfork bifurcation, transcritical bifurcation and all this, it does maintain a symmetric structure, oftentimes it does not, meaning there is a distinct hysteresis. Even if you try to model the present coronavirus, the what is known as the SAR model, you will see that such models are also, while they are not exactly such very simple models, but there are simple models which can help you understand how the population will grow, how the number of infected people will fall and so on. So, with the help of these tools, I am pretty sure you will be in a very comfortable situation on understanding all the different aspects that go behind modeling such systems, and not just modeling such systems, but extracting a lot of information from those systems. Information such as what is the equilibrium point, what is the growth rate, when will the growth rate cap off, when will it start decaying again, things like this. Such kinds of aspects you will be able to discuss, and that gives you more insight into the actual dynamics. That helps you to make strategies, make decisions, what to do, when to do. That's a very important question. You may have seen that everything has a certain time. You cannot just stop everything and hope for the best. There's always an optimum time which you can prove mathematically as well. So, a lot of things go behind the scene in developing models, but oftentimes the simplest models are the best. And why are simplest models the best? Because they help you in assessing the physics of the problem, they help you understand the asymptotic behavior of the problem without completely losing analytical tractability of the problem. In many of the problems that we have done, we have looked at not just what the numerical solutions will be, but we have actually worked out a great deal of analytical information prior to solving them numerically. And that analyticity is quite difficult to do if the model itself is quite contrived. It has to be simple, but it cannot be too simple. There are cases where in attempts to make the system too simple, you lose out on certain physical phenomena which actually you are looking for. And usually what happens is you have a certain set of observables and then you feel, okay, let me see what kind of mathematical model can help me sort of arrive at such conclusions. But then the lacuna may be there, and it is the task of the modeler to understand the lacuna. And such tools that I have shown in Python, Octave, they play a very major role in addressing the entire parameter space, so that whatever model you have made, you can sweep through those models quite quickly and efficiently. And one such example I would like to cite is where we use sliders to understand how the jump catastrophes occur. Imagine you don't have such kinds of interactivity. So, it becomes quite difficult to assess or judge whether a certain model does give the end behavior that you want. And in fact, such kinds of interactivity which Python allows you through the Jupyter Lab platform, it's a very sort of convenient way of extracting all the information of the parameter space from the system. Many of you had, not many of you, some of you had doubts in installation of Node.js and all these things. And let me tell you, these are quite generic, meaning it all depends on what kind of operating system you're running, and sometimes it also depends on the browsers. But most of the times it should be fine. Node.js and all these things are needed for utilizing the IPy widgets, which I find tremendously useful. So the key point that I am trying to say is, have a look at how to install Node.js. One of my TAs has already highlighted on how you would go about addressing those installation issues. In the end, it all depends on the operating system that you're working on. On Windows, it's usually quite straightforward. You just download the exe and start working. On Linux, it's also quite simple. On Mac, I have no idea because I don't use a Mac. So it is essential nowadays to install all these kind of tools, because even if you use a different programming language such as Julia or Sage Math or whatever you want to use, nowadays the emphasis is on having a background kernel and a different front end, and typically the front end is opted to be that of a browser. And the reason why it is better to use a browser is because it removes any dependency of any GUI related issues. A browser is quite generic, something like a Mozilla Firefox or Google Chrome is good enough. And such kinds of notebooks, well, I cannot really pinpoint who popularized this notebook, because this kind of a notebook environment has been there since the days of Maple. Mathematica, of course, heavily utilizes this kind of a notebook system, and with the whole ecosystem of Node.js, it has now found its way into programming of not just Python or Octave. There are a host of kernels that you can use. You can use Julia, or nowadays it is also there in programming of microcontrollers such as Node-RED. Even that is based on the Node.js platform. So that's something which is worth looking into. And regardless of whether you are able to install Node.js or not, just keep in mind that you can run each and every program without even having to use Jupyter Lab or Jupyter Notebook or any other IDE. You can simply make a notepad file or other simple text file, name it as .py, that is a Python extension, or an Octave extension which is .m, and you can simply execute the file from the command line by writing Python 3 space your file name. It is as simple as that. You don't need to really go deep into the aspects of Jupyter Lab and all that, because I thought, because it's a good environment for documenting whatever I am saying and writing programs and showing figures, that's the most convenient for me to teach. That does not mean that it has to be done that way. You can of course write C program, or rather Python programs standalone and execute them from the command line. So once again, I wish you all a very good evening, and I'm open to questions. If anyone has any questions, you can feel free to ask. So one aspect I'd like to discuss real quick about writing programs, and I've been writing programs live for you, and you might have seen that there's a certain chronology towards writing a program. There's a certain way that I develop each program, and it all depends on how clear it is in your head. And at the end, I mean, programming is not something which is to make your life miserable. It is something which helps you translate your own thoughts into something which a computer can do. The better the coherency between you and the computer, the better will be your experience. And we have always started off by scribbling down something on our notebook and then making sense of what we need to do. Once we are absolutely sure, we then start programming whatever we need to achieve. And never think that a program has to be done in a single go. Oftentimes, when you are working in research related topics, there is no well known answer to whatever you are doing, and that means that invariably you will run into issues. The point is to always keep a lot of debugging and a lot of checks. So, by checks, I mean certain snippets in place which you know will give a certain answer given a certain input. It is very important to understand that code verification, or rather code testing, is a very important task of programming. And while that is not the goal of this present course, it is something which you should always pick up in case you are writing programs in C. Then you must look into debugging or tracing memory leaks. There are sophisticated tools available for that called as Valgrind and all these things, Pylint. So, always try to make sure whatever snippet you are writing, it gives you a correct output given an appropriate input. It should not be the case that you are giving some correct input but it is giving you garbage output. So, that check itself is a very important step in testing, in debugging. Whenever you are stuck, you can be assured that these are the sections of the program that run quite well, and you can easily pinpoint where the issue will be so that you can debug quite quickly. So, debugging is a very important aspect of writing programs, and is not just restricted to Python, C. It is in fact quite generic as well. It all depends on on the flow chart that you make. Okay, what the conditionals will be, what the if else statements will be, how you have it in your mind, and how you will translate it to the computer. That is how you can pinpoint issues. Another aspect that I have not really done but I have touched upon is writing pseudocodes. So, pseudocodes are function blocks, conditionals, statements that you write in a human readable form. What do I mean by a human readable form? For example, if you want to have a coffee, then you go to your kitchen, you see that there is no coffee. So, if no coffee, then go to the market. So, it is like a human readable statement telling you what you need to do. And then once you have the entire sequence, you can simply start plugging in the different pieces of code. So, Swati says good evening, a very good evening to Swati as well. Do you like to ask something to me? Or? So, I will wait for a few more minutes. I am looking forward to any questions you may have. You can post them on the forum as well. You can mail me, it does not matter. It does not have to be live right now. But whatever it is, I will be more than happy to address them. All the questions that you have posted on the forum, I hope you found them satisfactory, the responses that I have made, and I hope you can make real progress in this. The whole task, not the task, but the whole aim of this course is to enable you to undertake research which would involve programming, which would involve some kind of logic, and I hope this course enables you to really undertake those. Please feel free to ask anything that you want to, regardless of how easy or difficult it is. I'll try my best to answer those so that your learning is unimpeded. Okay, I am aiming to study mathematical modeling and computational mechanics. Excellent. Would you like to ask me something? Okay, good. So, computational mechanics often involves topics which are not restricted to but are heavily dependent on finite element methods. So, finite element methods is a class of methods in which you solve partial differential equations on grids, and these need not be uniform grids, they can be irregular grids as well. So, the basic difference between finite difference methods and finite element methods is that you are trying to actually minimize some kind of functional, and such functional based techniques they enjoy the added advantage that you can have a global, or you can have a domain in which you have very few elements, but even though you have very few elements, you are still able to achieve a low error, although the local behavior will be quite unpredictable. So, in computational mechanics, often you would start off with learning finite element methods. Most of what we will be studying in weeks 6 and 7, they can be easily extended to understanding how finite element methods work, how you can achieve discretization, and even though you may not do the discretization or the solving on your own, it will add a lot of value, a lot of insight once you understand how the assembly of the matrices takes place, how the constraints are put, and how different kinds of relationships happen between different elements. So, mathematical modeling is quite broad, but computational mechanics is a topic which actually has a lot of interdisciplinary research as well. Imagine if you want to analyze how a blood cell, red blood cell flows through fluid. So, that involves understanding the interaction of a red blood cell with the fluid itself on one hand, and how the red blood cell will actually change its shape because of the flow or because of some disease. So, the analysis of the membrane, how rigid the membrane is. So, the membrane is like a solid, a deformable solid, while the fluid is interacting with the deformable solid. It is like a fluttering of a flag, for example. These kinds of problems are called as fluid structure interaction. Hello, Dr. Gupta. Nice to meet you. Thank you for asking. And please, don't hesitate to ask any questions that you may have. Give me some feedback on how you're finding the course so far, how you've been finding it useful in your daily research or daily academics. I would imagine that all these tools in scientific computing would be quite important when you are doing the process of learning, where for example, if you're learning fluid mechanics, you can easily plot all the streamlines, you can find the path lines, you can do all sorts of things. It can really enhance your learning. When you are studying heat transfer, for example, when you study the heat transfer from a fin, so you can plot how the temperature in the fin varies in space and time. Things like that you can easily apply, and while no one would ask you to do that, but it is always a big plus when you do it yourself, and that really reinforces your learning. So let me share with me if you have any such experience, or if you have if it has enhanced your teaching in any way or learning in any way. Just let me know. thanks a lot for your feedback. I really appreciate it. I'm very happy that you find the lecture materials useful. Okay. Might be there's some issue in the internet, but my voice should be clear. There should be no issue. All the lecture materials are available on my website, and I've posted the links in all the videos. I have posted the links. All the lectures, whatever I've covered in the lectures, whatever program I've been writing, and the counterpart in Octave, all of them are available on my website. Please have a look. I will post the link on the forum as well, on the Google group. Hi Bhanu, would you like to ask something? So all the course material is because these are codes, and I don't want people. No, I have not shared the PDFs. I have shared the HTMLs. You can download it as a PDF. Shouldn't be a problem. So one question is MATLAB and Python similar? And the answer is both yes and no. MATLAB is rather more similar in operation to Octave, and Octave is often is touted as being a clone of open source clone of MATLAB. But yeah, I mean, most of the things you will find in MATLAB, they are also there in Python as well. So if you have a very strong sense of logic towards addressing a problem in Python, you should be in a good position to address that problem using MATLAB as well. But the only thing is, because MATLAB is sort of, it requires you to have a license. That is one of the reasons why I would not prefer programming in MATLAB. But yes, MATLAB is incredibly versatile. If you have access to MATLAB, you can get a lot of things done quickly. But thanks to a lot of developers who have been developing Python libraries such as NumPy, SciPy, and a host of other libraries including Pandas. So these libraries really allow you to do rapid prototyping of your program without having to spend a lot of time, and it's all free. The best thing is it's all free, not a single penny spent. But yeah, I mean, conceptually they are similar. For example, MATLAB has linspace, Python also has linspace. MATLAB has log space, Python also has log space. Okay, and data analytics using MATLAB is one thing. Data analytics using Python, there's an entire module for that called as Pandas. So the community is so dynamic. The Python community is so dynamic. Whenever people face troubles, they come up with solutions and they make it available for everyone to use. And that's the beauty of it. It's not something which is closed source. Anyone can contribute, anyone can have a look. So that's a very good question. For computational mechanics, should I go with C++ or Python? Python is good for quick prototyping, for quickly seeing whether whatever logic you have developed is correct or not. But once you go on to big systems which require a lot of elements, lot of memory, I would rather prefer C or C++. In particular, whenever I do problems which involve huge matrices, I would initially develop something on Python, see if it works properly. Once I am convinced it works, for scaling it up, I would write it in C. And PETC offers all those libraries which help me to make matrix assemblies, to solve linear systems, to solve large sparse systems, and these are some of the topics which you will see in week 6 and 7. So yes, I mean speed, memory usage, they are much more efficient in C and C++ rather than Python. But Python gives you a very quick platform to start developing your programs and understanding what the nitbits of it. Well, that's a good question, very good question. Oftentimes people also do one thing, they write down a program in C, then you can use Python to call that program which you have written in C, so that in the front end you have Python, which is quite easy to use. In the back end you have libraries written in C. So you get that ease of entering values or defining your problem, and you at the same time you achieve the massive speed because you have written on the core of the program in C. Important languages for computational mechanics. Well, you would be in a very good position if you know Python, C or C++. And you will encounter Fortran now and then, but once you understand the logic behind writing a program in C, C++ or Python, you will see that writing a program in Fortran is not that difficult, it is just a matter of understanding the syntax. So once we go beyond the syntax, you will see that yes, writing down programs in other languages is also easy. And that is how we all started. I just started learning C initially, and now whatever as the world progresses, maybe somewhere down the line there will be a new programming language, maybe Cobra, something like Python, who knows. And if it is good for your purpose, why not use it? But at the end of the day, it will all be how coherent you are in your head and how you can apply that coherency to translate it so that the computer understands what you want to do. It is like a communication between you and the computer. So I am quite happy that someone in the second year they are learning so many things. It brings me great joy, and it's quite heartening to hear about students who are learning new things, who are trying to apply their knowledge to different areas, who are motivated to undertake such kinds of difficult problems. I am quite happy. Any other questions? I am open to any questions you may have. Alright everyone, thank you for joining me in this live session. In case you wanted to ask something but you could not, please feel free to post it in the forum. I will be more than happy to answer them. And with this, I'll see you next time in the next live session, but you can see me in the recordings. And I wish you all a very good evening and goodbye. See you again.